So
Okay, so we're like I say, we're going to start some new stuff here. It's strongly related to the stuff you've already been doing. It just builds upon chapter 5. And I know some people still need to finish up chapter 5. We'll be in the lab tomorrow. Those who are done with everything can work on the new assignment I'm giving you, and those who, that's next door. Those who who need to finish up the test, that's fine. You'll have a couple days in the lab this week. Oh, just so you know though, this isn't a big deal, but progress grades do come out. I don't think it's a big deal, because really the progress grades, I've said this before, I'll probably say it again, they're kind of silly, really, with our grades being online the way they are. I mean, by the time your parents get the progress grades, they're going to be outdated. And so, just so you're aware, though, just in the event that it is a big deal, the grades, what I will do is I will give you a lab day tomorrow, and then I won't upload grades until after the lab day tomorrow. Okay, on the test.
Oh, the test in the grade book?
So the test will go in the grade book. I'm not sure if I'll put the last one in there or not, just because I'm not sure everyone's gonna have time to get through the last one, but I'll for sure put in the first 2 tests into the grade book.
What are those?
Those are the 2 non-graphing ones. Wouldn't you agree the hardest one is the first one on solving equations?
Maybe.
Oh, the second one? Second one, you think? Okay. Okay, well, maybe it's the second one then. But those are the two that'll go in there, which is kind of unfortunate, because the third one is really easy. Yeah, I mean, and so, within a few days, by the end of the week, the third one will go in there, and that's going to certainly help out a bunch. But like I say, I mean, really all you've got to do is just, even if you didn't get through one of those tests and your grade looked a little bit grim when the progress grades go out, I'm sure by the time it gets home, you just got to say, okay, look, Mom and Dad, there's what it is now, and it should be fine. Make sense? Okay. So, using properties of exponents, we're going to start to talk about the topic of chapter 6, the next unit, is polynomials, and we'll get into that more tomorrow. But in order to, and polynomials are really important. Polynomials play a huge role in science and engineering and mathematics. But before we jump into those and start to explore polynomials, and really quadratics are just polynomials. They're second degree polynomials, and we'll see why here shortly. We got to refresh our understanding of properties of exponents. This is stuff you already know. This is not going to be a hard assignment. This really is review, maybe sort of advanced review, but it's stuff that I'm sure you've all done before. Okay, so properties of exponents. If we assume that a and b are just any real numbers, and m and n are integers, okay, so before we go any further, what's that mean? Give me examples of what numbers a and b could look like. 4 and 5. Okay, give me examples that illustrate all the different kinds of looks they could have. 4 and 5 would work. What else? -5. What else? 5/4 could be a fraction. Good. What else? Could be an irrational number. Give me an example.
0.3 repeating.
0.3 repeating. Okay. Pi, square root of 2, square root of 5, anything that can't be expressed as a fraction is an irrational number, right? So decimals that don't repeat, don't terminate. Okay, make sense? Okay. So all of those are examples of a and b. Those are real numbers. What about m and n? Those are integers. What do those have to be? They have to be whole numbers, or they could be positive. Whole numbers would be 0, 1, 2, 3, 4, right? What else could they be? They could be negative, right? They could be positive or negative whole numbers, right? So those are just the dashes on a number line, so to speak. Okay, but if we take a and b and m and n to have those descriptions or those constraints, these are just the properties of exponents that you know and love. The product property. We know that if we multiply like bases, what do we do to the exponents? We add the exponents, right? You know that. What if we take the power of a power property? What if we take a power to a power? what do we do to the exponents? Multiply the exponents, good. The power of a product property. If I have a product of bases taken to a power, does this make sense that I can distribute the exponent to both bases? Okay. And then we have the sort of the, oh, I guess this too, the negative exponent property. We know that a negative exponent on the top of a fraction is equivalent to what? No? Give you an example. So if I have something like this, if I have 3 to the negative 2, how could I write that in terms of a positive exponent?
0.2.
No. Okay, yeah, a negative exponent on top means a positive exponent on the bottom. So that would just look like 1 over 3 to the positive 2, right? Okay, conversely, this one isn't shown up here, but conversely, we can also say something like 1 over 3 to the negative 2 equals what? 3.
No, 3 squared.
What do you think? Well, that's going to be 1 over.
3.5.
That's going to be 1 over. Really, this is just 1/9, isn't it? Everybody agree? Well, this is going to be 1 over 1/9. What do I do if I have a fraction on the bottom? I flip and multiply. So what's the answer going to be? This is equivalent to 1 over 1/9. Well, what is that? 9, right? How do we get that directly? 3 to the positive 2. The moral of the story is, a better way to think of this negative exponent property is this. A negative exponent on one part of a fraction, by part I mean top or bottom, is always equivalent to a positive exponent on the other part of the fraction. So a negative exponent on the bottom is equivalent to that power written with a positive exponent on the top. A negative exponent on the top is equivalent to writing that power with a positive exponent on the bottom. Okay? Make sense? Okay, that's important because the assignments you're going to be doing, typically the problems are going to say write your answer in simplified form using only positive exponents. Okay, so that's going to be a key one. All right, the zero exponent property. I keep going too fast here. The zero exponent property, this is kind of a weird one, but anything to the 0 power is always equal to 1. Yeah, it's equal to 1, with the one exception of 0 itself. 0 to the 0 is undefined, indeterminate. But any other non-zero number to the 0 power always equals 1 every time. Okay? And then we had all these properties up here that had to do with products. We have the corresponding properties that do with quotients.
Okay, borrow doing this for a second.
For a real quick second, sure. We have all the corresponding quotient properties. So what about this? What if we said when we multiply like bases, we add the exponents. What happens if we divide like bases? So like this, I've got a quotient of like bases, a to the m over a to the n. What's that equal to? You subtract. Okay, now I want to show you something here. Really, this is just a combination. The quotient of powers property is really just a combination, whoops, not of that one, of the negative exponent property and the product property. Let's take a look at why that is. Okay, so if we have something like a to the m over a to the n, how could I write that in terms of a negative exponent? That a to the n. I could write that as a to the negative n on the top, couldn't I? Does that make sense? Because a positive exponent on the bottom is equivalent to a negative exponent on the top. Agree? So that would look like a to the m times a to the minus n. And now if I use my product property, we know that if we multiply like bases, we add the exponents, right? So this would be the same thing as a to the m plus negative n. And plus negative n is the same as minus n, right? Okay, so we could have come up with that pretty easily with stuff we already knew. Now, there is a better way to write this one, though. There's a better way to think about this one. There's sort of a new and improved version I like to have students use rather than this one. Okay, because this one, I'll show you why. This is fine if we say a to the m over a to the n equals a to the m minus n. That's fine. And that applies in situations like this. What if we have x to the 7th over x cubed? What's that equivalent to? X to the 4th. Good. Okay, but what about a situation like this? What if I've got x cubed over x to the 7th? What's that equivalent to? Yeah, that's x to the 3 minus 7 to the minus 4th. And if I want to write that in terms of positive exponents, what do I have to do? Yeah, I've got to flip that into 1 over x to the 4th. So really, I think there's a better way to write this, a more efficient way to write this property. We could write it instead as a to the m over a to the n equals a to the m minus n, but it also equals 1 over a to the n minus m. Which one of these do we use? It depends on what's bigger, m or n. Kind of the working rule is when you divide like bases, what you do is you keep the base in the part of the fraction where it has the most power, and you subtract the other exponent from it. Does that make sense? So for example, on this previous example right here, where we had x cubed over x to the 7th, well, where does it have more power? In the bottom. 7's a bigger exponent. So we'll keep the base on the bottom and we'll subtract the top exponent from the bottom. Make sense? Then you can just do it in one step rather than two. Okay? Questions? All right. I don't know if you've seen it that way before or not, but it's a good way to think of that one. And then wrapping this up, we've got the equivalent of the power, the power of a product property. We have the power of a quotient property. And that says essentially the same thing we said before. If I have a quotient of bases to a power, I can distribute that power, that exponent to the different bases. Okay, so let's look at some examples of this and just how we simplify things. So what do we do with that?
25 to the 9th. No, yeah.
What's it going to be? These are just, now I'm going to get a number answer for this, aren't I? But we want to get to our answer in the easiest possible way. So I have some options. I could turn this into an enormous negative number and turn that into an enormous negative number. Or actually, that'd be positive, wouldn't it? Sorry. Yeah. And multiply those out. But is there a more efficient way to do it?
Yep.
What is it? Yeah, negative 5 to the 9th, exactly. We'll use the properties of exponents first to get negative 5 to the 9th and just evaluate the base ones. Okay? Okay, same thing here. You know, we're just using that property. It's actually 5 plus 2, piece of cake. Okay? What's this?
2 to the 12th power.
2 to the 12th power, good. Which we can evaluate one time. Okay? Let's get through that. Okay, this is an example where it really pays off. This is negative 5 to what power? Negative 5 to the what? Okay, the whole thing, though, would be negative 5 to the negative 2. Good. What's the negative 2 mean? Okay, so what's my final fractional answer then? Okay, and what is negative 5 squared? 25, so I get 1/25. Yeah, good. Okay, well, what's that? X squared, good. Okay, what about this? What do I do first here?
Distribute.
I have to distribute. Following order of operations, I'd like to simplify inside the parentheses, but I can't. right? They're not like bases. So if I distribute, I'm gonna get r squared, and on the bottom, what am I gonna get? S to the negative 10, aha. So what's our final solution look like then, our final expression?
R squared plus S to the negative, I mean S to the 10.
Plus S to the 10?
No,
Times, good. Okay, so the S to the 10th comes to the top, and it just looks like r squared S to the 10. Okay. What about this? What do we do? I mean, what can we do here? What's the order in which we're going to simplify this thing? We're really just going to follow order of operations. So say it again. Exponents first. There's nothing inside the parentheses to do, but if I apply the exponent, what am I going to get? What's it going to do? What's this second power going to do to those factors inside? Okay, I'm going to get b to the negative 6. What's 49? 7 squared. Good. Okay. And now what? Once I get a negative 6 there, what do I do? Yeah, good. I've got like bases then, don't I? I've got the base b shows up 3 times, but it doesn't matter if I'm multiplying a string of factors together that all have the like bases. I can add them all up at the same time. So I just get b to the negative 6 plus 5 plus 1. What is that?
0.
Okay. What is b to the 0? 1. So what's my answer? 49. Good. Okay. Okay, if I want to write that in terms of positive powers, what's it going to be? Yeah, and this is where I'm going to take a different path than probably the PowerPoint does. How would we do this most efficiently if we want to write this in terms of positive powers?
1 over x.
Yeah, keep the base on the bottom, subtract 5 from 10, and, oh, I guess I remember I fixed that one, yeah. Scientific notation, just quick review. I mean, I'm not sure why this always comes up in this section, but it's a good thing to review. Remember how to use scientific notation? What are the, if I want to write that, that's kind of an awkward number to write because it's so big. How do I write that in scientific notation?
1.314.
Okay, good. So when we write something in scientific notation, we have to write it in terms of some base times 10 to some power. What has to be true of this base, the number that's being multiplied by 10 to a power? What's the smallest it could be? 1. Could it be 1? It could be 1, but it can't be less than 1 if it's going to be written properly. It's got to be greater than or equal to 1. Could it be 10? No, not if it's going to be written in its proper form. It can't be 10. It's got to be less than 10, right? It's going to be greater than or equal to 1 and less than 10. And how do I come up with this exponent real easily? What's the rule? Yeah. Good. You can just count the number of places that the decimal has to move from its original location to its final location, right? If it's moving to the left, we count that as a positive power of 10, which you just associate with a big number, right? 10 to the 11th is a big number. Okay, so how many places do we move it? 11, right? Piece of cake. Okay, what if we had something like this? How could we do this? Why might scientific notation be of some value to us here?
Because we could do it happy.
Move it to scientific notation, do the small numbers.
Yeah, good. We could divide much smaller numbers, good. Especially if we're estimating. If we're just trying to get, which a lot of times we are in science, we're just trying to get estimates. So I could write both of those numbers in scientific notation. And then I could estimate the quotient of the small numbers, right? And then the powers of 10, I have like bases there, don't I? 10 to the 11th over 10 to the 6th is just 10 to the 5th. Okay, and so I get something like, roughly, if I divide those out, it ends up being roughly 0.25. We can just say 0.25 times 10 to the 5th. And so how would I convert that back to normal notation? What would I have to do?
The decimal 0.5 places.
Yeah, good. I'd have to move the decimal 5 places to the right to undo the scientific notation. Yeah, I mean, you know that stuff. Okay. Let me look at a couple quick examples from the assignment. A few more challenging examples here. So, what you gonna do with? answer in the best form. This isn't a real hard one, but what are we gonna do with this? What's the property that's gonna apply first? I gotta distribute, don't I? There's nothing I can do inside the parentheses, right? But if I distribute this power to all three of these factors, what do I get? Well, we can write it in terms of negative exponents first. So what do I get? 4 to the, okay, 4 to the negative 2 times Okay, so how do we write that then? I want to write this in terms of positive exponents. So where does the x to the negative, or where does the 4 to the negative 2 end up? On the bottom, and what's going to be the magnitude of that? 4 to the second, so 16. What about the x's? Those stay on top. What about the y's? They go to the bottom. So that's the way to write this. Okay? That is what we call a rational function. We'll get into more details about what a rational function means. The true definition of a rational function is it's a ratio of polynomials, but we haven't talked about polynomials yet. So that's how we want to write this thing. Now, I'm going to be really particular about this because I'm going to ask you to write these things in the simplest form. And that doesn't mean equivalent to the right answer, but I want you to write them in the simplest way. So I would argue that writing this like, well, first of all, you have to write it in terms of positive exponents, but even doing things like writing like that is unnecessary, isn't it? There's no reason to do that. Adding those parentheses jumbles this up, and it's going to make it a little bit harder to read. And as you get into bigger and bigger rational functions, you really don't want to, and more complicated than rational functions. When we start to add in chapter 7 some radicals or fractional exponents in there, you really don't want to have all these extraneous symbols in there. You want to write it as compactly and neatly as you can. And so I've designed these problems so they would take off a little bit of credit for even doing something like that, because I wanted it in its simplest form. Even stuff like that. Do I need that time sign there? No, I don't. It's implied multiplication if I just put the 16 next to the y to the 8th, right? Okay. How about something like this? What if we had now what? I could distribute. I could. I'm going to get the right answer. Is there an easier way to do this one? I can simplify inside the parentheses there, can't I? Right, so I could write that as, before I even apply that negative 5, what's going to become of everything inside the parentheses?
X plus 4
You're going to get
over 2x.
x to the 3, okay, because I've got 4 minus 1, right? Over 2 over 4 reduces to 2 on the bottom to the negative 5. Now I can distribute that negative 5 on the outside, right? There's another little trick. I could distribute that to both parts, but what is this? See if you can tell me. What is a over b to the negative m power equivalent to?
B over H and power.
Yeah, does everybody see that? That's the same thing. Now we're going to skip the middleman, but that's the same thing as saying 1 over a over b to the positive m. And if I have a fraction on the bottom, I just flip and multiply. So really we can just go straight over to this. So the moral of the story, a fraction to a negative power is always equivalent to the reciprocal to a positive power. That's a good shortcut step. So maybe one thing we want to do here before we go any further is what?
2 over X to the
Yeah, write it as 2 over x cubed to the positive 5, and we end up doing less work that way. Okay, so then what's our final answer look like?
32 over X to the
Yeah,
negative
2 to the 5th, which is 32, over x to the
15.
15, because I'm taking a power to a power, right? So I have to multiply the exponents. Okay, you get the idea? Okay. If there's any other real tricky kinds of things you gotta do.
For that trick, the trick that you showed, the reciprocal of it,
Yeah.
wouldn't that only work if, both sides only had like, positive exponents? Like if they had a negative exponent on the top or bottom half of it?
Right, so you're saying, okay, I see what you're saying. How about if we change that last example, so it was, what if we had 16, 6, what if we had 16x to the minus 4 over x squared to the negative 2?
And that end up all on top?
Almost. Yeah, so what's gonna happen there? Is that what you were saying, John? Is that what you're suggesting, something like that?
No, I mean, like, could just like, get the reciprocal and then positive exponent.
Right. So the example we did, we first simplified this so it was written in terms of positive exponents inside, and then we flipped it. I think what you're saying is, what if that had been like a negative 3? Right, then it would have made sense probably just to distribute. But if we always do that first step where we rewrite the stuff in parentheses in terms of positive exponents, what's this gonna look like? If I just focus on what's inside, does that fraction reduce? What's that reduce to? So I got an 8 on the top, a 3 on the bottom, right? And the x's, where do they end up? Okay, x to the 6 on the bottom. 2 is bigger than negative 4, so I subtract negative 4 from 2. And now I can flip the whole fraction. Right? So what do I end up with? Not 3 though, it'd be 3 squared, so 9x to the over. Okay. Oh, I know, one last one. I mean, I think you guys are fine with this. You're gonna, it seems pretty simple, I'm sure. You're gonna have a few questions, and that would be expected. What about one like this? What if I had, what can I do inside the parentheses? Simplify. Okay, what do I end up with? 2x cubed, okay. So I just get 2x cubed. I don't get anything on the bottom, do I? Okay. If I take this to the negative 3 though, what's that gonna do?
1 over 2x.
So I get 1 over 2x cubed to the positive 3, so what do I end up with? I get a 1 on the top, don't I? Do I have to have the 1 on the top? Yeah, I do, don't I?
8.
X to the 9th. Now, what if this had been a positive 3 the whole time? Then I would have just ended up with 8x to the 9th. Would I have to put a 1 on the bottom? Should I put a 1 on the bottom? No, I shouldn't. Right? That's making it more complicated than it needs to be. Okay, you got the idea? I think you do. We're good. Do we have any time left over here?
It's till 28, and it's like.
28. Do we want to go